Could you tell us a little bit about what you conceive of as a theory of everything and what you think that means and consists of?
Theories of everything purport to explain every physical phenomenon. So the way you falsify a theory of everything is to bring forth a well-established, well-known physical phenomena, which is not accounted for by the basic assumptions and postulates, equations of a particular theory of everything. That's how you would falsify it. I attempted to falsify binary mechanics right at the beginning, back in 2011, and failed. And every hypothesis that I've tested so far has confirmed that binary mechanics was making the correct predictions. So I haven't been able to falsify it yet.
From your point of view, a theory of everything, as I see the current situation in physics, well, we have a contradiction. We have quantum mechanics and we have everything else, so to speak, classical mechanics, if you will. And quantum mechanics looks to be, it's not deterministic, it's indeterministic, while classical physics and the Newtonian conception is deterministic. So you have a big difference there in terms of, it looks like it's an irreconcilable difference. Quantum mechanics looks to have required that you have an absolute rest frame, whereas classical physics claims there is no rest frame. And these are significant problems, and they haven't really resolved those difficulties. So a theory of everything should resolve these differences, I would assume. Correct?
Correct.
Okay, now I did notice that yesterday Nick sort of objected to the idea that there's an absolute rest frame, which seems to be one of the fundamental postulates of your theory of everything, binary mechanics. Correct?
Yes, without an absolute reference frame, there's no way to determine whether a particle is in motion or not, except in that absolute reference frame. And in my experiments in the simulation of cooling a simulated volume containing various energy quanta in it down to absolute 0 Kelvin, all particle motion stops. There's zero motion. And at that point, we can then state that we have particles in whatever is there in the ground state. And I was stunned to find, as a principal investigator in this, some of the slides that I showed you yesterday, I was sort of stunned and amazed that these things were actually occurring, such as the definition of the 8 elementary particles postulated in the spot cube model of space, and that was actually confirmed in such a dramatic way. In fact, Nick pointed out that I misspoke, saying that the incidence of these particular patterns corresponding to the 8 elementary particles was 20 times, not twice. I was saying twice. I misread the slide. It was actually 20 times greater than the random distribution. So that here we're actually talking about creation of things from what? From the equations. That's all there is, input.
I'm doing comments on your talk from yesterday. You were talking about this gentleman, Jerry, and I forgot his name, that you...
James Hughes,
James
the MIT
Hughes.
Student.
Yes, right.
James Hughes, yes.
Until you mentioned that, I was kind of mystified by where this binary mechanics came from and what the idea behind it was. And I think that's a fundamental thing that you should actually start off by talking about that. And I suddenly then began to get an understanding of where you were coming from when you told that story. So I think that's an important piece of information. The other thing is,
thank you for that point. I think you're absolutely right, because that gives some of the human color to the story. In the continuous space-time model used in Dirac's quantum mechanics of the 20th century, I emphasize that because we're now, of course, in the 21st century, there's an infinite number of points. We have 8 different probabilities coming out from the 8 complex results of the matrix equation when you combine 2 relativistic Dirac equations with opposite handedness, which led to the definition or the prediction of the existence of the positron, which was then later discovered. Hughes showed that by rotating, now rotation of matrices is a very basic thing to computer programmers, and I've actually written programs to rotate matrices and so forth. Rotating matrices is a very basic thing that mathematicians and statisticians do. James Hughes showed me on the blackboard in my kitchen that if you rotate Dirac's 8x8 spinor matrix, what you get is the vertices of a cube.
Could you bring back that slide? Okay, now one of the things I noticed is that your bit function has 3 bits.
Here's one spot. All of the 8 different spots here in the spot cube, each of those has 6 locations. There's 2 locations in each spot unit for the 2 different kinds of quanta. When I was quantizing the complex amplitude in 20th century quantum mechanics, which only gives you probabilities, as everybody knows, I did not want to discard information because this work in 20th century quantum mechanics was producing results.
All right, hold on a minute, Jim. There are 6 faces to the cube, right?
There's 6 faces to the cube, but there's 6 locations in the spot. Okay, so that's 2 to the 6 configurations of the electron spot, for example, that I'm pointing to right now with my cursor.
Really, we're into complexity very much in a hurry.
Just think how complicated it is if you had an infinite number of points. Each one of these 6 locations that I'm pointing to here in the electron spot can either be 1 or 0.
Right.
So if that's true, then we have 2 to the 6 possible configurations for the electron. And you're saying, oh, that's complicated. Well,
you just explained it. Now I understand it better.
Well, thank you. Now let's go back to pre-binary mechanics where we have continuous space and time. How complicated is that? Because in this volume, which is L is about 2/3 of a femtometer. That's the dimension here. And so we have a cube here for the electron, which is 2L cubed of volume. Now consider that in everyone else's view, there's an infinite number of points here that we have to worry about.
Okay, well,
so if you're talking about complexity, binary mechanics is simple dimple compared to the kind of complexity that the people who are promoting continuous space and time are trying to foist on us. We're overturning the apple cart for all of those people who studied all that advanced mathematics all of those years. Because now, in binary mechanics, you only need 3 math ideas that even a 3-year-old has mastered, because these 3 ideas are intrinsic to being able to speak and understand a language. And that is the binary number, 1-digit binary number, yes or no, 1 or 0, up or down, right or left, full or empty, the binary choice. That's 1. Second is the AND function. If you look at the equations of binary mechanics, it's simply performing an AND function on different binary values to get a result. And lastly is the NOT function, where we convert a 1 to a 0 or a 0 to a 1. That's the NOT function. So those 3 math ideas that even a toddler knows, that can speak basic sentences, you have all the math that you need to understand 100% binary mechanics. All of the stuff about complex amplitude shown in this slide currently being displayed is just the origin of how all of this developed and where it came from with James Hughes' analysis of the spinor matrices of a pair of Dirac equations of opposite handedness that he showed when rotated actually gave you the coordinates of a cube, the coordinates of the vertices of a cube. Now, how could that be? Most physicists will agree with this statement. When you rotate a matrix, you haven't changed the physics, you just changed the point of view. So when Hughes, these mysterious spinners with imaginary numbers in them, the I there in here that I'm pointing to with my cursor in the complex amplitude, these curious spinners turn out to be all real number vertices of a cube when this 8x8 matrix is properly rotated. So that which is the true physical interpretation? An 8x8 cube of space or these imaginary numbers? Hughes was saying it's the cube. And he postulated, not me, he postulated, I'm giving him credit. I don't have to. I could steal his ideas, but I don't want to steal anybody's ideas. Hughes said that he thought that space was actually a lattice of these cubes. My
lattice.
part.
Okay, lattice. All right. Gotcha.
A lattice, that's correct. And so my part was simply to say, well, okay, James, if you're right, I couldn't find anything wrong with his matrix rotation. I've actually written computer programs to do that and could, if I wanted to, write the computer program to do the rotation that James Hughes did on my blackboard in my kitchen. The next obvious question to me is, what is the size of these cubes? How big are they? Let's pursue this and see where we go. And so then I lost contact with James. He went his way in life. I think he went to Africa, actually. I then developed binary mechanics based upon full quantization of everything. I just said, let's just not quantize space. Let's just go the whole thing.